The next semiconductor device that we need to look at is called the Bipolar Junction Transistor. This is a semiconductor device that's used to switch or amplify current signals, and it's commonly represented or called a BJT. A bipolar junction transistor has three terminals that are called the collector, the base, and the emitter, and there are two different types of bipolar junction transistors that depend upon the semiconductor arrangements that are used. So this is called an NPN or a PNP. And while we're not going to delve into the semiconductor physics behind how this works, we're going to touch on it just a bit. But the transistor is a fundamental building block of all modern electronic devices. So having some idea of how it operates and what the abstraction model that's associated with the bipolar junction transistor is going to be important. So how does a bipolar junction transistor work? Well, a bipolar junction transistor is a combination of two diodes, essentially. An NPN transistor consists of an N-type material, a P-type material, and an N-type material. They're all joined together. And there are different regions. One of the N-type sides is going to be called a collector. The other is going to be the emitter. And in between here, the P-type is called the base. And we represent an NPN transistor like this, right here. Okay, we have a slightly different symbol for a PNP transistor. And the way I always remember this is the arrow is not pointing in, so this must be an NPN. And of course, the NPN transistor refers to the arrangement of the N-type and P-type materials. Now, what we can do is we can look at what happens if we were to connect this transistor with its three terminals into a circuit, and into a circuit arranged so that the voltage between the collector and the emitter is much greater than the voltage between the base and the emitter. And remember that the voltage is a measure of the Fermi energy level difference between these materials. Now, if we were at thermodynamic equilibrium, all of the Fermi energy levels would line up with each other, and there would be this significant barrier to electrons traveling across this p-type base right here. But as we apply a potential across them, we're going to inject current into the base, and what's going to happen is we're going to get a net flow of holes and electrons through this material from the emitter to the collector, or from the base to the emitter. Without going into too much detail about this, essentially what's going to end up happening is that we're going to get, as we're injecting current and we're injecting applying a potential to the base here, we're going to get both positive charge carriers, holes, moving from the base to the emitter, as well as electrons moving from the emitter to the base. So that creates a net current flow in this direction. And the total amount of current between the base and the emitter is going to be increased because of this addition into the of current flow into the base. So our net conventional current flow is going to be from the collector to the emitter, and we're going to control how much current goes through this by what the potential is across this that is applied to the base relative to the emitter. And what we can see is that this acts kind of like a gate right here. And this is a gate to the flow of electrons. And that's the reason we call it a gate, is because when there's no potential difference between the base and the emitter, then the Fermi energy levels are going to shift to be about the same, and we're going to have a very large barrier to prevent, a very large energy barrier to prevent electrons from moving through the base. But as we apply a greater and greater potential difference between the base and the emitter, then we're going to lower this potential energy barrier. All right, and the gap right here is going to be lower, so more and more electrons can move from the emitter to the base and over to the collector. All right. So again, without getting too much into all of the semiconductor physics behind that, what we want to do is we want to develop this abstraction model to tell us how bipolar junction transistors operate. So we see right here we have an NPN BJT, And we have a PNP, which is just like what we discussed, except now the primary carriers are the holes, and it has a slightly different configuration to it. We also, the way I remember this as being a PNP is that the arrow points in, so PN, the arrow points in toward the base. Now, the way that we're going to create this abstraction model for a bipolar junction transistor is that we're going to model the collector, the connection between the collector and the emitter as being a dependent current source. And that dependent current source is going to depend upon how much current we can get through the built-in potential between this, between the base and the emitter, which is a diode with some small built-in voltage potential, VBE. All right, so if we can cause a current to flow through across that built-in potential that's due to that diode formation there, the amount of current that will flow from the collector to the emitter will increase by this factor of beta. And for most bipolar junction transistors, beta is going to be somewhere between a value of 20 and 200. So the bipolar junction transistor acts as a current-controlled current source. So we're going to try to force a current in this direction to increase the current between the collector and the emitter. Thereby, if we have a large amount of current here, if we can get a large amount of current injected into the between the base and the emitter, then this is going to act like a wire because it's going to allow a lot of current to pass through. If we get no current to pass through, this is going to act like an open circuit. So in a way, we can make this act like a switch. And we can see that here with our plot. The model is only valid for what we're calling the active region, where the active region is talking about the region where where the voltage between the collector and the emitter, which is plotted on the x-axis right here, and the voltage and the current that is allowed through the base to the emitter is, the current through the collector is plotted on the y-axis here, and then each of these regions, each of these blue lines, represents the how much current is passing from the base to the emitter. So for each of these blue lines, we have different operating points, and you see the more current that we inject into the base, the more current that we get through going between the collector and the emitter. And this is only valid in this region. It doesn't hold in these in the purple region right here, where we have a very low current that's being injected when we have a very small base current going in between the base and the emitter, or when we have a very small voltage between the collector and the emitter. But for the most part, we can approximate the behavior of a bipolar junction transistor well over a wide operating region using the abstraction model that's presented right here.